We'll start with some problems. First of all, why you need neural networks. The problems with, we will say, machine learning. So let's try to list out, let us say, some 3 to 4 or 5 problems that you people feel machine learning will not be able to cope it up. Any idea? So it's always good to know the problem and then go on to why are we doing that. So any idea what machine learning is lacking, or
when there's a large data is one thing.
okay? So you are saying data size is an issue. Yeah.
Yeah.
All right. Fine. We'll see how to put this as a problem. Anybody else?
When we have non-numeric data.
Okay. So I will say non-numeric data. Perfect. I was looking for this.
When we don't have enough features.
All right. Featuring issues. Good. Anything else? Corrections. Do people see that? Do we have, I think we have only 2 algorithms available in machine learning who are actually capable enough to correct themselves. Correct? What are those algorithms? We have SVM and boosting. Do you people remember these two?
Yeah.
They have a capacity to learn. Yeah. So this is one issue. Our ML is, an algorithm which we have to train and then we can use it. It does not have auto healing or auto correction system kind of thing, right? And fifth one I will say is somebody already featured non-numeric data. So I will say, what if you want to process a sequential data? So like I was looking at one of the codes sent by Ashish. So Ashish, you have used LSTMs there. So are you frequent with LSTM?
First time I used the LSTM. So actually I worked on, I read a lot of, watched a lot of videos and read a lot of articles on LSTM.
Okay. So you have an idea of LSTM, right?
Yeah.
So this is one of the purpose. So guys, what is like what are these things is, if you see our machine learned stuff, I cannot say this is a sequential data. Sequence in the sense, I showed you people ARIMA, for example, time series forecasting. That was a sequential stuff. Sequence means what happened some 10 years back, there is chances that at the same month or same time, the same thing might happen, the seasonality part of it. What if I want to take care of something like this onto machine learning? Sometimes it is not possible to do it. And there are hundreds of more reasons out of it. So I will say for our cause, the best reason could be non-numeric data. What do you mean by non-numeric data? Say pictures, say text, say voice. We cannot process it. Up to some point we can process using machine learning. After that, we have a limitation here. All right. So now what we are going to do is, let's try to build some algorithm into machine learning. See, also one more thing is, even though in our course we say machine learning is over, but actually machine learning is the whole box under which you have 2 parts or 3 parts here, which we call it supervised learning, unsupervised learning, reinforcement learning. After that, we have something called artificial intelligence, and then I will say some mixed bags of algorithms. Yeah. So still it's a part of ML only, but from now, what we are going to do is, say I have a box. I will not say what it is. We have some empty box here, and I'm giving some input to that box. Yeah. So let us say my input is defined like this. Now, when I give an input to this, I'm expecting a certain output. So before I get an output, I have some expectations. Let us say my expectations are EXP. I'm getting an output here. I'll say expected output, otherwise we get confused. Now, what we are going to do is, we are going to analyze this output. Is it as per our expectation or not? So how do we analyze? Let us say we analyze using a function. I will use a function basically to operate on our output versus expected output. All right. Now, if this function is of certain value, let us say the 2 values can be good, another one value could be bad. Let us say if the function is in bad value, what are we going to do? We are going to go back and make some corrections to this box. Now, what made this output bad? Can I say this particular box made it bad? Because of this box, we are getting some unwanted junk over here. Agreed, everybody? Yes. So what is our duty back? Go back and try to fix it. You keep doing this till we come to the phase which we say good. We'll come to this. What are these things now? But till we find that this and this is matching, I keep reiterating this. This is what is an example of a neural network. A very simplistic approach. All right. Any issues into this?
No.
Nope. Okay. Now there were two paths that you people observed here. One path was called forward path. Forward path was where I gave my inputs and this box amplified it or de-amplified it. We don't know. The box made some changes on it and gave us an output. This is called forward propagation. Now, since we found out that this function is of not a good value, we went back and we corrected our box. This is called back propagation. As simple as this. All right. So these are the most important parts within your neural network to understand. That we will give some input, we'll get some output, and we'll keep training it till we are satisfied that yes, we are getting expected output out of it. Okay. One more example. I usually give this. It's a very silly example. Let us say this is a kid, for example. Okay. And you are teaching some tables to the kid. Say you have taught 5 tables. Yeah. So while giving input, the kid is learning. Yeah. So you did something such a way that the kid knows the table. Now you asked the kid 5 5s are, for example, and the kid says 5 5s are 32. So what do? Immediately we go and correct. We keep doing it till the kid comes and says 5 5s are 25. This is also another example of neural network. A forward prop and a backward prop to correct it, and keep doing it till you are happy with the answer. Okay. Now let's talk about that box that we were talking about. Now what exactly is this box? So just give me a moment. I will open up my PPT and then we'll fire up.
One question here.
Yeah.
Basically, when we go for the backward correction, in that case, it is assumed that we know the input as well as the output, and we are putting into the box and verifying that whether the box is giving me the output. But in the case of prediction, we really do not know, basically the future prediction, we really do not know the output. So how does this really work?
Okay. So for any machine learning, whatever box I showed you, whatever we did, supervised, unsupervised, AI, reinforced, whatever we saw, the very first phase of any machine learn technique is machine learning, basically. So for that, we need a set of independent data and a set of target data. No matter what you are doing, if you are doing text processing, if you are doing voice processing, image processing, no matter what, the input matrix remains same. All right. So what you have got some input for training. That is, we call it as independent data. Then you have got some tags. You remember, guys? Y actuals, right? This is what will be our reference point. And whatever we get output, we will call it as Y pred. Say, we are going to compare always Y pred with Y actuals. Always, no matter what algorithm you're doing. And then if you are asking me of future predictions, once our machine has learned, once the difference between both of them is reduced to our satisfied level and the machine is learned, you have to disconnect this. You have to disconnect our input and you give only your futuristic output, which will be only your independent data, so that you will get Y. All right.
Okay. That's more of a learning phase, what you...
Exactly. Perfect. Yep. So this is a common stuff for all the machine learning, no matter what it is. The first thing we have to make it learn. Now there are some algorithms like LSTM and all that I was just talking about. Yes, in those things we can predict something without learning much of it, but we'll come down. So when we come to NLP, we will look at this. Let me not confuse you guys right away. Okay. For now, this is what is the architecture we are going to look like. Now there are some questions. Let me see. Okay. All right. Okay, so now let's go to this PPT. How to interpret neural network. So let's keep let's take the inspiration. This particular topic is being picked up from biology, okay, and neither of us are expert onto that, so we will make our own version of neural network. Let us say your brain neurons, the neurons that are there, and please remember, there is no neuron in your brain which is not connected to other one. Some or the other way it can reach from here to, let us say, to some other neuron. Yeah, so that is the first part of it, which is called fully connected neural networks. This is the basic of all the neural networks. That means each neuron is connected to all other neurons in the network. All right. Now let us say you divide this into 4 parts. This is part number 1, 2, 3, and 4. Now, when this brain was newly formed, that means when this was a baby, at that point of time, all these 4 were of almost similar. These zones were not differentiated. Now, what are these zones? You may ask me. Let us say this is my happy zone, for example. This is my sad zone. Okay, we'll not compare it with real biology, because if we do it, we are going to fail onto that. So I'm just showing you certain neurons belong to happy, certain onto sad, certain onto, say, relaxed part of it or sleepy part of it, and certain onto the anxious part of it, for example. Okay, let us say when the baby is newly born, they have not seen much out of the world. So what they do is they mix up all the emotions. Sometimes they keep crying, sometimes they're happy. They don't get it. Now, when a lot of events happen, day-to-day life, and the person grows up to some level, there are certain learnings that the person does, and the person tries to store those learnings in each of these neurons depending on the zones. So let us say at the age of 13, if a kid passes with a very good score, definitely the neurons over here will be active. All right. So please remember, a neuron can be activated and a neuron can be deactivated. That means in the happy phase, all of these will be deactivated. All right. They don't continuously keep running. The electrical signal is sent from one to another one only in certain trigger situations. All right. So this is what is the theory behind why we use neural network. So from here, now we will try to put this, whatever I said, onto the machine part of it. So let's see. So what basically you will learn at the end of this particular session is intro to neural networks, working of a neural network, forward propagation, backward propagation, and types of neural networks. So we will see to this on a very detailed, because now whatever 4 or 5 months you have from your course, we will try to explore almost every type of neural network available in the market. All right. Now, next one is what exactly. So I explained you what is a neural network. Why do we use neural networks? So please remember, it's a very simple. Neural network can adapt to changing input. So the network generates the best possible result without needing to redesign the output criteria. What do I mean now? Let us say, for example, we take a linear regression. Yeah. In linear regression, if we have baselined our equation, you people remember this equation, right? I think we started our interaction from this session itself. Yeah. Now, is it possible for me to change the inputs? If I change the inputs, will this work? We are not sure. If the inputs are very close to what we trained it on, yes, it will work. If they are not, it will not work. This model will crash. What if I tell you that there is a possibility of making a machine learning model? No matter what you are going to give me, I will relearn myself always, and I will deliver it output. What if I have got a self-learning kind of stuff? Yeah. So I will say this is more robust to changes. This is more adaptable. And this is more quicker in the terms of learning. Yeah. So this is where you are going to need your neural network. So the box that I just drawn on the whiteboard, that was nothing but your neural network. Guys, do stop me if you find it difficult to understand. Yeah. Now, next one, what is the application of it? So basically, I hail from deep learning background. This is what I do on my daily basis in my job. Now, you can use deep learning for anything. Whatever you have done so far, classification, regression, you can do the same thing on neural network. So the first thing I will say is decision making. That is your prediction and decision making. Second thing is, if you want to go a little more complex, you can talk about image processing. So what do I mean by image processing? So Let me quickly show you.
Then do you think the DL is much better than ML?
Yes, definitely.
Okay.
Definitely.
Then why the people use ML then?
Yeah, I'll tell you why. Why do we do that? Just give me a minute.
Okay.
Data science, contents, deep learning. No. Yeah. So now let me take you guys through a very simple application of neural network. It is not simple to code, but yes, down the line, we are making it more and more simpler. So just give me a minute. I have too much actually over here. Contents, deep learning, image recognition, okay, and image. Let us say I have a screenshot from a particular movie. All right, so this is a screenshot for me. Now, I want to automate certain things over here. So I will give you an example. If you people are on Netflix or Amazon, if you click on the star cast, the particular scene which is going on, they will match it up who is there in the particular scene, and they'll give you the description of the star cast. Have you guys observed that? If you stop the screen immediately and check for the star cast, especially on Amazon Prime, you will get the names of only those people live who are there in the scene. Have you seen that?
No.
Nope.
Yes. In Prime, you get to see.
Correct. How do they do it? Very simple. What do we do is when you click onto that Starcast button, no, Amazon Prime uses its own image recognition system and tries to create a boundary. Okay, let me use a different color. Tries to locate a face in the image. You would have also seen these kind of stuff nowadays flying around on YouTube. If you are talking about AI, no, they will see people who are walking, and they would have made one box around the people who is walking, and they would have said this is a person who's walking. It's become a trend now to post all these things on YouTube and LinkedIn just to show that, oh, I work on AI part of it. Yeah, but it's not rocket science. We are going to learn down the line. Now, this is what I want to do. So how to do this? Very simple. First of all, you need a big corpus. Corpus means a backend data saying that we don't know whether we'll get image of this lady or not. We don't know whether it's there in corpus, but yes, we will get lot of images of men and women. And if it is a men, the tag attached to it. So if I say the independent variable is men, the target variable attached to that will be men. That is, the image is men, the target variable tag to it is men. So this is how I tell my neural network that I am giving you an image as an input. You have to adjust your whatever is inside such a way that you have to give me. So whenever I give you this image, you are supposed to tell me it's a man. So this is how we do it. So let me now show you how do we do it. So this is an untagged image. Let me try to copy the name of the image, and now we will try to push some kind of brackets onto it. Yeah, let's see. So all I need to do is, this is my version of image processing. Okay, so just hold on for a minute. Our kernel is dead. Just give me a minute, guys. Why am I showing you this? Is so that you'll get to know why are we learning deep learning. Otherwise, if I would have started with neurons and all, it will be the same as our video. Notebook. Documents, data science, content, deep learning, image processing, code, image. Yes, and here I will paste our image. Okay, it's processing. Yes, it is showing me there are two faces that he has detected. Did you see that? And later on, if you go and see here, this is my output image. Right? It is very simple. It is showing me and we have detected two faces here. The next version of this could be find out who the celebrity is. So what we have to do, we have to give an input corpus of all the celebrities, and we have to retrain a network saying that if you get this particular image, whoever this actor is.
All right. So this is how Amazon and IMDb and all these people do it. If you want to take one more example, let us say we take a complex example. Look at this image. It's pretty huge, right? So what I will do is I'll try to push it across through a neural network. So just let me copy the name of the image. We'll import it. So this is a pre-trained neural network. I'm not if you observe, there is no neural network running here. Why? Because my neural network is currently lying into this particular format. You don't have to keep running your neural network every time. You can store it, pickle it, and whenever you want it, you can export it out. In this case, I have an XML file which does my job. Now, if you take some time, because there are a lot of faces there, and it will show me how many faces are detected. If you observe, he's saying we have 29 faces detected. Let's go and see the output. This is how the output looks like. Yeah, and you will observe some of the faces are not detected. Can you spot those faces? 1, 2, 3, 4. What is common between all these faces? Can I say they're tilted? Yes?
Yeah.
So there is no box around it.
Yeah.
That means the corpus that I've used to train this particular neural network needs me to have a straight face or full face. For this particular person, the full face is missing. All right. So this is how this is the end application of a neural network, I will say. Clear? We'll go deep into it so down the line in computer vision session anyway. So this is how we do image processing using neural networks. Okay. Speech processing. So I can talk something, and from the corpus, the network can pick up and it can tell me what I spoke about. Okay. So not sure if you have seen this earlier, but just give me a minute. Documents, data science, nope, contents, deep learning, great learning. Yeah. So this is my speech to text converter. So just observe, I will talk something, and after once I talk, it will populate here and it will tell me what I spoke about. All right. So hello everyone. Hello everyone. Yeah, it's weird. Hi everyone. Yeah, so did you observe? It said hi everyone. If I say some of your names, say Raju, Ashish, Mohit. Raju, Ashish, Mohit. Yeah, did you see that? So how does it take it? What are we doing is basically we are running some kind of Google audio in the backend. So it is not only understanding what I'm saying, but is also trying to translate it and more. So basically this particular bot, what it does is it's a payment bot. So if I say pay 300 or 500 rupees, it identifies what I'm saying and then tries to pull out the money out of it. Yeah. So this is one more application where you can use your neural network for voice bot, text part of it. So text is not in our certification context, but I will show you guys down the line how you can use this for text also. Yeah. Again, gaming, I'll say it's a very big industry. When it's out of my scope also, it's very complicated. And on the futuristic next 5 to 10 years, you can expect something like this to grow up. So I'll give you one example. There is a startup who is working on an eyewear for visually impaired people. So that particular eyewear will recognize what is going around the world. So let us say the person is sitting in a park. So if he wears those glasses, the glasses will analyze what is going around in the park. And those analyses will be sent via voice to the blind person, saying that there is a dog who is white colored, he's running. There are 3 kids who are playing a football. It looks like it is going to rain. If the person is walking, it will caution the person. I'm able to see there is a car coming, please hold on. So whatever challenges he has because of no vision, they can overcome this. So probably next 4 to 5 years, you can expect this to be very common. So computer vision and AI is working towards this. So this is where you are going to use this. I'm not sure how many of you are going to actually work on this industry, but yes, a very good place to work in for next 5 to 10 years. Now, coming on to the real part of it. Now, what exactly is a neural network? We saw all the applications, very good. Now, this is how a simple neural network looks like. This is an example of fully connected neural network, FCNN, because if you observe, each neuron is connected to all the neurons in the next layer, right? Each neuron is connected to all the neurons in the next layer. So we are not leaving anything, we are fully connecting it. Now what actually happens, let me show you. So what we do is we give an input. Now each neuron, or sorry, each line that you see over here has got a weight, some random number you can say, which gets multiplied to my input and goes to the next neuron. The whole game over here. So if I ask you now, let us say we talk about some of these machine learned algorithms. Let us say we talk about SVM. Can somebody tell what exactly we learn in SVM? We give some input, right? We train the model till it learns, and then we say, okay, the model is trained. So what is those things that we are learning in SVM? If somebody can highlight that.
The pattern and the input.
Perfect.
Pattern, series, whatever, which can define the whole pattern database.
So let me show you a small clipping, and after that we will go on to an Excel file where we will simulate a neural network. Okay, so just observe this clipping for now, and then we will see what happens. Okay, so you will observe there is one number 7, which if you observe this number 7, we have divided this 7 into some kind of pixels or numbers. Those pixels and numbers are going in the first layer as an input. Okay, and if you observe, some of these are on, some of these are off. So if I rewind it, yeah, so this is my some layers in the box, and this is my output. So if I give a number 2, you will observe this particular neuron will come as an output, saying that I have identified that the image belongs to number 2. Now the image will belong to number 1. So this one will be highlighted. So this is a very simple example of classification. Do you people agree? This is what we do in machine learning also, right?
Yeah.
We classify. The only change here you guys will feel something new is, how do I fragment this number 7 into the inputs, how I give it to them, what happens here, and how the output is there. That is what is the today's challenge. I will explain you guys how it happens. Another way of understanding a neural network classification could be as simple as this. If you observe, there is one image of a dog which gets penetrated into some of the environment, and finally I say it's a dog. This is how we do object detection. You give any object, if the neural network is trained on that, it will be able to identify, no matter what breed, what angle we have taken the photo, whatever it is, you will be able to detect that it is an animal, which is a dog. Okay, so now there are 3 layers which are most important here. One is called the input layer, one is called the hidden layer, and one is called the output layer. Now let me shift you guys to that Excel file, and we will simulate something. So we'll start from scratch. Yeah, how does a neural network work? As I said, we have 3 layers: input, hidden, and output. So please remember, as we are talking about neural networks, the complete operation, whatever it is, it should be in the form of numbers. No matter if we are dealing an image, or we are dealing voice, or we are dealing text, whatever it is, image, number goes in, number comes out. Yeah. So let's see how it is. So the first thing is your input layer. So represents the dimensions of the input vector. Now let us say I have a data set which looks like this. Our machine learning data set. It has around 1, 2, and 3 columns, independent data. And this is my target data. Yeah. So if I have 3 columns, that means I am supposed to have 3 inputs to this. That means each neuron in input represents 1 dimension. All right. Good. And each neuron in the output represents my target column. So let us say in target, if I have 0 and 1. So this neuron is supposed to detect 0, this neuron is supposed to detect 1. That means if I give a combination, let us say the combination of 0, 0, 0. That means when all three of them are 0, it is going to highlight that this is your classified output. Okay, so this is input and output. This is how we decide input and output. Now comes the hidden part of it. Now, what exactly is a hidden layer? Hidden layer is randomly, I will not say randomly, but it is our choice that how many neurons we want here, how many layers. Some of them have 10 layers, some of them have 2 layers, 4 layers, whatever. These are nothing but the same neurons, but the only thing, they are connected in some other different way. All right, so we've got 3 layers: input, output, and hidden. Any issues onto this? Simple. Don't worry about the calculations. We'll see. But so far so good. All 3 layers are okay. Okay,
fine, fine.
Now we'll talk about something called activation function. Now, what is an activation function? If you observe this PPT carefully, you would have observed that not always all the neurons are on. Did you see that? Some of the neurons are off. Correct? And in output, other neurons are off, only one neuron is on. So you might be wondering, okay, how this happens. This is the job of activation function. Activation function acts like a switch. Now, let me define one activation function right away. Let us say we will design a function which says if my number is greater than 1, then I will activate that. I will say pass the number to the next neuron. If the number is less than 1, I will say switch it off. Now, in my input, if I give a number of 1.2, what's going to happen? This is your function. You will choose this one and you will say that the current neuron is active, pass the number to the next neuron, allow the number to pass through. These are called activation functions. This is a simple one I have shown you. Okay, let us dive deep into this activation function theory. So there are so many functions available like this. We'll go one by one. Before that, let me show you what happens in the neurons. So imagine this is one neuron, this one, and this neuron I have represented here. For example, any of the neurons, all of the neurons have same kind of look. What am I doing? I'm giving some input to a neuron. This is my input, x0. There is a weight, and if you ask me what is this weight, I will say randomly chosen number. Okay? During your forward propagation, when your network is built, we randomly assign some number, say RANDN, and we put some number. Yeah? That random number gets multiplied with your input to become W0X0. That W0X0, from the other neurons, we get W1X1, W2X2. So these are inputs from other neurons. All right. All 3 of them are coming and converging here. So if you want to see an example, just have a look here. So if I say we are talking about, say, this particular neuron, how many inputs are coming? 1, 2, and 3. So this is my X0, X1, X2. All right. So you can imagine that way. Now, inside this cell, inside this neuron, what do we have? We have an activation function. We call this as an activation function here, F. And also there is one random number called bias, which we have to add it with our addition of all 3 of them. So if you observe here, what is this? W0X0 plus W1X1 plus W2X2 plus some random number called biasing factor. All right. Now, if this particular operation is greater than certain value, it is allowed to pass. If it does not satisfy my function, it is not allowed to pass. Okay. Now let me show you what are these functions. So if you observe, we have got, looks like very complicated activation functions, but actually they are very easy. We'll start with the easy function, this one. Have a look at this. Unless and until your output is greater than 0, it will be, or else it is 0. This is called step function. Second one is sigmoidal function. Have we done this earlier in any of the algorithms? Can you recollect this? Have we done sigmoid in anywhere else?
Logistic regression. Logistic regression.
Okay,
Logistic
good.
regression.
Correct. Log R, and one more then. kernels?
Yeah.
SVM kernels, you remember? One of the kernel was tangential sigmoidal kernel. Yes? What does it mean? If your input is between, say, this phase and this phase, it will continuously increase. If your input is less than this, the value will be 0. And if your input is more than this, it will be a static value of 1. If you expand this a little bit more, okay, and one more thing, this is not ReLU. I don't know why have I written ReLU here. This is wrong. This is sigmoid. And if you expand this little more on the depth part of it, but you have to cross through 0, that becomes your tangential function. All right. Third part is called ReLU. Okay. So what is ReLU basically? Rectified linear unit. So if it is less than 0, it is permanently 0. If it is more than 0, it is a linearly increasing curve. This is one of the most popular activation function we are using actually. So depending on what type of inputs you are having, you can use one of these. So down the line, when I will show you guys how to write case studies and how to decide your networks, at that time we will try to choose all this stuff as per our data. Yeah, and there is one more important activation function called softmax. Whenever you have a categorical output, now we just saw that there are two types of possibilities over here. The output could be categorical and output could be regressive. Correct? The same thing we have done in machine learning also. If your output is categorical, the default function, activation function you will use only on output layer is called softmax. It is a categorical activation function. If in case you have no categories, you have regressed outputs, regression as an output, in that case you can use any of these. Are we clear? All of you?
Yep.
True. Yeah.
Yep. So what are these functions and all, we will see when I show you the stuff. But for now, are we clear? We have sigmoid, and ReLU, and threshold. These are some of the most important ones. And why do we need it? Just to manipulate our number and let it pass forward. That's it. All right. Now, moving on to, so this is how overall on a very high level neural network works. Now let's try to simulate one. So I have simulated a neural network in Excel file. Now let me show you what it is. Now please, we cannot do this on a higher level, but on a very simple neural network, you can train it up. Now, observe my network. So as an input, what do I have? I have got some alphabets from A to Z. Now please remember, computer does not understand what is A, what is Z. What we do is we do somewhat cheating at the back end. We tell the computer that if this is the number, it should be displayed as this figure. If I get this as a number, it should be displayed at this figure. Everybody agrees to that? Yeah, binary logic and all, if you have studied in the computer science and all, this is what it is. Same thing applies in neural networks also. So say, for our sake, what I've done is I've taken A to Z and I have divided numbers between 0 and 1 in 26 equal distances. All right. What is my job now is, my job is to train a network such a way that when I say that WHY, okay, in English spelling, it should also give me the same numbers as an output, but in the form of numbers. And then we will map it up in the form of digits. In the form of letters. All right. Now let me show you what exactly are these calculations and what we have done here. So before that, how many inputs do I need? So if you remember, I say total number of independent columns is equal to your inputs. In this case, can I say I just have one independent column, which is A? Agreed? So I will need only one input. How many outputs do I need? It is, okay, first of all, what is it? Is it a regressor or a classifier? It is a
classifier.
Look at the numbers. Okay, one way you are right, because we are passing ABC, but in this case, we do not have softmax in Excel file. So what I've done is I've made a regressor, and then later on we will try to classify it. But perfect answer. So it's a classifier with one output. So this is one input, one output. All right. And then you may ask me, okay, what are these other things? These are my hidden layers. We will see down the line what are these and how I designed this. All right. Now let's try to pull one number. Say I pulled out W. what is W equal to? 0.8472. That is what my actual value is. This is my actual Y. All right. Now, what I'm doing is I have to choose some random weights. Do you people remember? We talked about weights, randomly chosen data. Now, let me randomly choose some weights. So I will make it say 0.8, 4, 5, 4, 2, 45, say 80, okay, 67, some random number, whatever we like. All right. So I have chosen some number as my weights. Now, what are my weights? Where do my weights lie? My weights will lie on each of this line. So this particular weight 0.7 that you are seeing is a weight given to this line. So when my input 0.8472 goes to this particular neuron, it gets multiplied with this weight. Are we clear onto that? Everybody? What are these weights? This is my biasing factor and these are my actual weights. Okay? Guys, do let me know. Are we okay with this? Any issues?
Yes,
No?
with the concept is fine, but just one thing I don't understand how this random number comes in picture, because when we say that the output is dependent on the input as well as the weight which is coming up. So the weight, the number which we are choosing for the weight is something which will influence the output as well.
Exactly. Perfect. So what is our job then? To back propagate and adjust the weights such a way that my actuals and my prediction should match up.
Okay, so basically that's part of learning in this case. So to correct the weight, basically. Okay.
Exactly. The whole game here is to adjust this weight such a way that the output that we get here matches my input. All right. Do you see now output and input matching? Not at all, right? Look at the loss function that I have put, RMSE. That is around 5,000 plus odd something. Agreed? So whatever weight
So,
chosen,
sorry, what is the problem that we are taking here? The actual and the RMSE you have, output that you have. What is the...
Yeah, we'll go down, Ramesh. We'll go down to that.
Yeah.
Okay, so the first thing what I did was I multiplied this with my current weight, and activation function I've used is sigmoid onto that. Now you may ask me from where I got sigmoid. Very simple. We wrote a logic here or a macro over here to simulate sigmoid. Now what is sigmoid? On a very simple scale, sigmoid is defined by 1 upon 1 plus e power of minus x. What is my x? X is one of my inputs given to the sigmoidal function. That's it. So what I've done is I have my own sigmoidal function where what I'm doing, if you observe the formula bar, E5 into this one, okay, got it? Yep, minus my this one, what do you say, bias factor, and I sigmoid it up. That means whatever manipulation I'm doing down the line, I am putting a sigmoid onto that. And when I put a sigmoid onto that, the value that I get is 0.012, which I have perfectly spoiled it up because my original value is 84 and the value which I do after multiplication is little weird. Okay, then so this is my N1 H1. Same way I take this up, multiply it with next weight, put a sigmoid onto that and get this. Okay, third one is N1 H2. So this one. So if you remember, if you see here now we are getting inputs from two of them. We are getting an input out of N2 H1 and also W3. Same thing. Whatever goes out gets multiplied with the new weight 3. We'll put a sigmoid onto that as an activation and we'll throw it out. All right. So our data is propagating from here to here. So when this particular data propagates from here to the output, it becomes minus 42. And if you ask me why, it is all because of junk weights that we have put. Agreed? Everybody agrees to that? The weights are causing this issue. Right? So what we should do now? If weight is responsible for making this issue, we are supposed to go back and change the weights. Now, how do we do this? In neural networks, we call it backpropagation. I will explain you with formula now, but for now, in Excel file, what do we have is inside data, we have something called solver. I don't know if you people have used it. My intention here is to reduce my RMSE. Now, everybody knows what is RMSE, right? root mean square error. It's a loss function. What do you mean by loss function? Difference between my output, predicted output, and the actual output. That is what we call as loss function. Everybody's okay with this RMSE? All right. Now, what is my intention here is to focus on my RMSE here. And my intention is to reduce my RMSE. Agreed? Yes or no?
Yes.
Yeah.
Yes. We'll go to the formulas now. After this, I'll show you in derivative way how to do that. Next, what is my intention here? What I need to change such a way that my RMSE should reduce? Can I say all of these junk weights? I've given those weights over here. Now let me click on solve. Okay, it'll take some time, but you observe the weights changed. And the weights, when the weights are changing, now can you look at my RMSE?
Yeah.
From 5,000 odd, it has come down to almost 0. Do you agree? 3.2 into 10 power of minus 6 is almost 0.
Mm-hmm.
Yep. And look at my output now. And look at my input now. Can I say they are almost in sync? Yes or no? So can I say I have designed a network here such a way that tomorrow, if I give this particular value, it is going to identify that it is W, or at least if I give this value, it is going to identify it is. Are you able to visualize that now? Let's test it. Let's try to test it. So for example, I have given a value S here. S is what? What is the value of S? Is 0.6931. Okay, so when I give the value, automatically all the calculations are done, and the output that I get is 0.6904075. How I got this? Using these weights. And the error that I currently get is 0.003, negligible amount. So this is your forward propagation, and what we did here using solver was your backward propagation. One forward plus one backward represents one epoch in a neural network. So neural network continuously goes front and back, front and back, front and back, till I find my loss function to be minimal, till my weights are adjusted to the very best values. This is the high level overview of neural network.
So the solver, whatever it did, right? So this is very, very easy and good to understand. The solver was just trying to adjust the weights and keep iterating, is it? Probably it would have done whatever 8 to 10 epochs to get the right value.
Correct.
Okay. How does it adjust that, or is there any way that it adjusts this?
Yes, there is a way to adjust that. So let me show you using formula. But before that, are we clear with two processes, forward and backward? Now, if I say forward prop and backward prop, you will be able to visualize what I'm talking about. Forward prop is your activation functions. Backward prop is adjusting your weights. All right?
How do you know you were two hidden layers, Krishna?
Yes, we'll come to that. We'll come to that one by one.
Okay.
But
so don't worry about how do we put it and how to choose this and all. We'll go deep into that.
And you also said that some of the neurons may not get active because the activation may not happen with all the neurons, right? So how do we demonstrate it in this example? Is there a way?
In this, it's not possible. In Excel file, we have a limitation here of only using sigmoid. So if I use ReLU, so if you look at my ReLU, where is our ReLU? If you look at ReLU, any value which is in negative will be switched off. Agreed? Yes or no? Will this ReLU allow us to pass any negative value?
No.
It will be clipped off. Very simple. You will see this in Python, Ramesh.
And one more clarification, Krishna. Can you just go back to that picture?
Yeah.
See, like from input to this NH1, this W1 is getting passed, right?
Yes.
Will the activation function work here, or from N1H1 to N1H2 only the activation function will work?
Activation function resides here, N1H1. The multiplication happens here, and then it goes to activation function here.
Okay, so from input, the activation function will not work. only when it goes
No.
to N1, H2, the activation function will get work.
Yes.
Right?
Yes.
Okay, fine.
Correct.
Okay, yeah.
Perfect. Perfectly
Yeah,
identified.
yeah, thanks.
All right. Good. Now let's come to some heavy maths now. So now you people might feel it's getting a little heavier. So what do we do? So let me explain you forward propagation in a more complex way now. So now when I talk about weights, layers, activation function, now you will be very clear. Okay, so now we'll not repeat what is activation function now. Let us say I have got a weight or input X. X gets multiplied with W1 weight of that line and I get alpha 1, which goes inside an activation function. I get alpha, which gets multiplied with my next weight and gets alpha 3. Alpha 3 or A3 goes into new activation function. It becomes A4. A4 gets multiplied with some weight and I get my output. This is your forward propagation. Okay. Now the same thing you can see over here. This is my input. This is my weight 1. And if you remember, I said there could be a biasing factor. It is again a random number. We use it. So this into this plus this becomes this. Then I pass this through a sigmoid function. So when I pass 0.81 through sigmoid, I get 0.6939. That is your alpha 2, this one. Same process happens till you reach your output. So if you now observe, our input actually was 0.84. And because of this, whatever we did in middle, we got some loss of 0.83. Right?
So one question here, this weights and bias numbers, what they have input here, is it just a random number or?
Random numbers. Okay. Random numbers. See, if I change it, if I change this, it will change. Did you observe? It's changed values.
It should be in a float only or any,
anything. Actually, float is better. Okay. Integers, there is a function which will allow us to put only integers, but then there are some problems with that. I will show you why. All right. Okay. So this is what is your forward propagation. Now, any questions onto this? How this value became this value? Any questions? Perfectly clear. So you imagine if there is a bigger network like this, say you have a bigger network like this. Now, if I ask you guys, you know what goes in and what comes out. Are you clear with that? Forward prop?
Yeah.
Yep, good. Now let's talk about what happens in the backward prop and how those weights are learned now. So before moving on to backward prop, I will ask you guys a very simple question. What all type of loss functions you people know so far? What are loss functions we know? Let us say at least 3 of them we'll talk about. What do you mean by loss function? Y-pred when compared with Y-actual. That's your loss function. How do you compare it? Subtraction.
Yeah.
Agreed? Distance. How far they are? Agreed? Yeah. MSE. Can I say RMSE? Yes, these are some of the loss functions that we know about, right? Now, let's come to the complex part of it. Now, how actually we learn the weights? Now, it was very easy for me to use solver and show you. Very easy because you have a ready-made function, it worked. But what happens in the neural network? How network understands this? So say, this is your output, okay? So this is what you are supposed to get. And sorry, this is what you got and you are supposed to get Y as an output. This is your actual, this is your predicted. So if I have a function which will take care of O versus Y, I will define this L as my loss function, okay? And what we need to adjust, you put the things which are in scope. So my current for my back propagation, only the highlighted part in red is in scope. That means we need to alter one of them or all of them or combination of them such a way that my loss function is decreased. All right. Now, which mathematical function helps us to do that? My intention is by how much my loss function will change if I alter these, what kind of function we can use here? From our school days, you can recall some functions. We have done this, you people know it, but we don't know the real application of it.
Differentiation.
Have you heard about it? Perfect. Perfectly identified. We will say by how much my loss function will change if I alter, say, weight number 5. Everybody is okay with this? Differentiations? Yes? It's a step function. So by how much I should change so that this will reduce. Very simple. Now, if I want to develop a chain rule here. Okay. Now, how do we do that? So now you may ask me, fine, we got a differentiation, but how do you say which weight to change and how do you derive the equation? So for derivation of equation, we'll put here. So it's not needed, but it's just for your understanding of backprop. I will say by how much my loss will change with respect to my actual output that I've got. Sorry, predicted output that I've got. That will be my first differentiation. Multiplied by how much my output will change with respect to my weight number 5. Agreed? Multiplied by, let's write the chain rule. How much my weight 5 should change with respect to my alpha 4. How much my alpha 4 will change with respect to my alpha 3. How much my alpha 3 should change with respect to my weight number 3. How much my weight number 3 should change with respect to my alpha 2. Agreed? Guys, you're getting it? How much my alpha 2 will change with respect to my alpha 1. And how much my alpha 1 will change with respect to my weight 1. Can we go anywhere further?
No.
No, right? Because weight and x is not dependent on each other in any way. Agreed?
Yeah.
Now just think about it. If you want to just focus on how much you should change this weight, what we should do? Cancel this and this. What are we left with? Can I say we are left with dou of L divided by dou of W5. Agreed?
Yeah.
Yes? Now keep cancelling it up. What if I cancel this and this gone, this and this gone. Now what are we left with? Can I say dou of L divided by dou of weight number 3? Yes?
Yeah.
Correct? Again keep changing it.
Yeah.
Keep cancelling. What are we left with? Dou of L with respect to dou of weight number 1. Simple? So now can I say I have got a method to find out how to control my loss with respect to all 3 of my weights. Same way, you imagine a larger network where there are so many weights, the same rule happens and the weights are optimized in the back propagation. All right? Simple now?
So we are changing the layer 1 weight.
You can fix whatever you want. So if you say you want to change all of your weights, you can change all of them.
Okay.
If you say I want to freeze this weight and change these 2, you can do that as per the chain rule formula. Right? Okay. For your understanding, for the first week, you can assume that yes, all of the weights are getting changed in one first back propagation.
Krishna, is this automatic calculation or do we have to specify in the algorithm?
Automatic.
Want to change?
Automatic. In Python, we have something called optimizers. They take care of, one line will take care of complete optimization. The way we did it in Solver, no, in Excel. Same way we have it in Python.
Okay, cool.
Yep. One line, that's it. Okay. So today I will show you a neural network which can be designed in 3 lines. That's it. A very simple neural network classifier. Very simple. You don't need to go very complex models. You can even do it a very 3 to 4 liner. That's it. Over. Okay. Now, any issues with backprop?
No.
No? Good. All right. So last one, just from my side, I know we have done this, softmax function. Can somebody tell me what was softmax again?
But one more thing, this all the calculations, everything, we need to practice or it happens in the Python?
Python. You don't have to do anything. So whatever maths I showed you, it is for your understanding.
Okay.
In Python, within seconds, you will be able to train your network. Right? Okay. Final one. No more theory. Now we'll go to practice. What is softmax? You people remember what was softmax? Okay. Softmax is an activation function. Please remember, don't forget this.
Yeah.
Softmax is an activation function to be used only when you have an output which is a classifier. If you have an output which is a regressor, you can use any of these.
Okay.
All right. And you don't even have to worry about the formulas. You just have to remember the name. That's it. One name in Python is enough to do all of your calculations. Good. So now can I say at least 30-40% you guys are clear on what is neural network?
Krishna, like this is Ganesh. Like softmax is mainly used for multiple categories, right? For
Correct.
a single classifier, can we use sigmoid? Will that be fine?
Yes, you can do it. For a single classifier, even you can use step function here.
Okay. Oh yeah. Okay.
Correct?
0. Yes. 0 or 1. Okay.
0 or 1. That's it. Even you don't want to use the classifier, no problem. We'll build a filter of our own. So we'll take the output and we'll say if it is this, answer is this, or it answer is this. Anything. But yes, you are perfectly right. For two classifications, where you have two classifiers, you can use any of these. Not a problem.
Krishna, one question is from the video classes that the professor has shown us. So in that video class, he told us that the reason why we don't use a step function and instead use a sigmoid or 10x because the step function has a constant value. So we would not be able to calculate the slope, and hence the gradient descent would not work the step function. My question is, why are we using ReLU, and it has become more popular because half of the ReLU is also a flat line and would not be able to calculate the gradient descent of that.
No. See, if you look at this, ReLU is continuously increasing.
For the negative value,
ReLU is not tracing, or ReLU is not parallel to x-axis. Did you see that?
Yeah.
Correct?
I'm
that is
for the negative value. For the negative value.
Negative value, it's flat. Correct. Perfectly right. So if you ask me why, yes.
Yeah.
So
if we are in the negative value zone, we would not be able to calculate the gradient descent and would not be able to move to the correct position.
No, in that case, I will say let me correct your approach here a little bit. Please remember, we are talking about a fully connected neural network. So if I go back, do you think this is fully connected? Yes. Each neuron, is it connected to the next layer? So even if one of the function is clipped out, there is another function which will help to pass it through. You getting my point? Let us say if this is a negative value. Yeah, this is a positive value. And let us say this was ReLU. In that case, you are perfectly right. If only negative value is going inside, it will be clipped off. But also along with that, we are adding one more value, which will allow us to go forward. Correct? Since we are having two inputs, there are chances that one of them is positive and it will allow us to go forward. That's it. Yes?
Yeah.
So once
the same concept would apply into the step function as well, isn't it? In the step function as well, one value is positive, one value is negative.
Correct.
So even if one value is negative, so it would allow us to go through the next iteration. But the way it was taught in the class, it was from the point of view of the gradient descent. So trying to minimize the loss. And in order to minimize the loss, we need to know the slope of or the gradient descent of the location where we are in the plane. And if that is a positive or negative, that would depend on where we need to go. In the ReLU function, half of the times we will not be able to calculate where are we in the plane and not be able to calculate gradient descent and will not be able to solve the problem from there.
Correct. Perfectly. So now let me come on to gradient descent. Yes,
So
you're
I just want to
perfectly
know
right.
if there's something else in the ReLU that I might be missing.
No, you are perfectly right on ReLU, and your analog is perfectly right on gradient descent. But I will try to reshape your gradient descent understanding once more, so that you'll be able to fit ReLU onto that. Yeah, but you are perfectly right. If in case we enter a negative zone, definitely you are not going to get anything out of ReLU. Okay, so let's now try to get a very detailed, or I'll say a sneak peek onto gradient descent. So what, as per you guys, is gradient descent? What exactly you mean by that? Can somebody quickly let me know? What is your understanding on gradient descent?
It's basically calculating the slope of where we are in a particular plane and trying to minimize trying to move into the right direction, whether we go into negative direction or into the positive direction, in order to minimize the loss or any function that we're trying to achieve.
Okay, perfect. Now let me reframe that. Let us say, let's not use too much technical term like slopes and all, because when we do that, people get confused. So let us say these are my weights. All right, and this is my loss function. There is one particular place where the loss function for this particular weight will be 0. Agreed?
Yeah.
Every weight has one point where the loss is 0, at least. Let us try to draw a diagram. Let us say we have a gradient descent diagram like this, for example. Okay, and also we'll drop a line over there saying that this is the line of optimal weight. Now there are chances that you might be here. When you chose a random weight, you might be here. So when you are here, your loss is pretty high. Agreed? Or else there are chances you chose a very high weight. We are not sure about it. At that time also, your loss is pretty high. In both the cases, as Raju was saying, is you have to either reduce the weight or increase the weight, direction of the gradient descent. In this case, my direction is towards right. In this case, my direction will be towards left. All right, depending on the slope and on whatever he was saying. Let us say there is one number, or there is one factor called learning rate. I tell my back propagator, whatever I'm going to use in back propagation, I tell him that every time you make a mistake, every time you get a loss, you reduce or you move by some number x. So every time I have a back propagation, my weight value goes by x values down, or in this case by x values in this side. This keeps happening till I reach a spot where the loss is in control, or I have reached an actual position of 0 loss. So this zone, what I kept, the lines that I kept here, these are called sweet zone. Sometimes it is not possible to reach here. Now I'll tell you why. Let us say you have chosen a value of 0.1. And let us say when you kept doing back propagation, one time you have reached here. Now if you add 0.1 to this, you are going to end up here. And if you end up here, what happens in next back propagation? You have to subtract. When you again subtract the learning rate, you are going to end up here. So this is what we call the oscillation zone. There are certain times because of learning rate, we will not be able to reach here. So in that case, we can say that we'll put a boundary saying that yes, we are okay with this kind of weights. This is what is my take on gradient descent. Are we all in sync now? I think you people also have the same idea in your mind, right? The only challenge here is to understand how to choose this and how many epochs on an average will take me to reach over here. How many back propagations will happen to reach over here. All right? Yeah. So Raju, one thing is you're perfectly right on ReLU. So it's going to clip the negative part of it. But also remember, we are not using only ReLU in the network. One layer could be using ReLU. Another layer could be using sigmoid also. One layer could be using softmax also. Since it is a combination of highly connected layers, it is sometimes okay to ignore certain neurons even if they are creating a mistake. It is okay. We can ignore them. And they will also not create much nuisance in back propagation because of this gradient descent formula. I hope you got my point on ReLU.
Yeah, I just wanted to know that there's something else in the railer. So just, thanks.
Oh, it was
clarified that.
Ashish. Oh, sorry. Okay.
Yeah.
Yeah, Ashish.
Yeah. Yeah, I just wanted to clarify that there's nothing else in the Relu that I might have missed in the Relu. Yeah.
So it is very good. I am very happy it is you guys, because my other batches were not very focused on activation functions. But it's very good to know this, because if you have a good idea of what is activation functions and when you use it, your neural network designing becomes very easy, because you have to hand make this neural network. Yeah. So you have to choose activation function there. Yep. All right. Perfect. Good. So now let's try to design one of them. So we are not done yet. There are some more concepts which I will show you one by one. So I think week 2 also I have covered almost using this. So I think your next week's video, the week 2 videos, will be very simple for you guys. Now, before moving on, I would like you to introduce to some of the libraries within neural networks. There are many actually. And now there is a big boom. Every company is putting their own library. Yeah. So the most important library for learning is TensorFlow. The latest version of TensorFlow now, it is just released. It is 2.0. I am currently working on 1.0. I am yet to migrate to 2.0. It is like you learned Python 2 and suddenly Python 3 was launched. Okay, so it is very critical for us to transfer this, because some of our codes are very heavy. And since this is new, I am also waiting for it to be stabilized, and I am also waiting for all the solutions available online. After that, I will migrate basically. The codes will change. So this is TensorFlow. What is the use of TensorFlow? TensorFlow is an end-to-end neural net library which is owned by Google. For now, it is free. Not sure later, but it is owned by Google. And what it does, it gives me the statistical power. So whatever forward prop, back prop, activation function, weights, whatever you saw, could be managed by TensorFlow. The calculations could be managed by TensorFlow. Good. And also, if you observe, there were certain hardware that we need. We need some virtual neurons who can hold the values, locations, right? Even TensorFlow can do that. We have something called TF-Learn, which can do that. But to avoid it, what do we have? We have a better version. We have got Keras. Keras is a high-level API which sits on the top of TensorFlow and simulates a neural network for us. Good? Are we clear? TensorFlow versus Keras. You can build a whole network here also without Keras. Why do I use Keras? It's easy to define in Python. All right. We have one more called PyTorch. Have you people heard about PyTorch anytime?
Yes.
Yes. PyTorch is a very powerful library. Very powerful. But the only issue with PyTorch is it's a low-level programming language. This is a high-level programming language. Like somebody just asked me that while doing backpropagation, do we need to do this manually? I said no. Why? Because I have a simple command which will help me to do it. Whereas in PyTorch, you have to hand build everything. Not now. Now PyTorch is evolving. Yeah. So PyTorch is again a very popular library for academicians and researchers. So maximum majority of the times when you look at an AI-based paper, especially from a university or a research company, they will be using PyTorch onto that. Why? Because they can hand make this thing. They don't have to depend on this. I am a big fan of TensorFlow. So whenever these upgrades happen, now I will be bound by this. I have to upgrade it. Whereas in this, you can hand make these things. But it's a low level one. It means you have to everything build from scratch. Okay. So this is PyTorch. Apart from PyTorch, there are so many libraries available. Like if I show you guys a library called Swift, for example. So whenever you want to deploy your AI onto iOS or Android, this is one of the most popular libraries. Sonnet. Sonnet belongs to one company called MindLearn, if I'm not wrong. And this company makes or publishes a lot of AI-based papers. You can use their codes to learn. The only issue is They do it using their own library called Sonnet. They do not use TensorFlow, Keras, and all that. So we have to depend on that. Like that, there are so many of them available. All right. So the most popular ones, if you see now, is for your starting purpose. These two are very good. Please learn them thoroughly. And after you master that, you can go on to PyTorch. So you have a complete exposure of all the libraries. Good. So these are the libraries. Especially, you should know the difference between those two. So I'll give you one example. Recently, I was taking an interview of one of the candidates, and when I asked him, he said me, I am from AI background. And this is the harsh reality of our field. Everybody says, yeah, I know artificial intelligence. So I very simply asked him, okay, what are libraries you are aware about? So he told me TensorFlow and Keras. Yeah. So I asked him that, can I use TensorFlow independent without using Keras? He said no. This is where people will pick you up, saying that you have no idea about AI. So out of 10 interviews that I take on AI, 9 of them I rejected because of these reasons. So people would have seen the codes, they would have done it. But if we don't know the basic difference, where to use what, then it's very difficult to build a network in AI, because it's not a straightforward method here, to be very frank. So guys, please be very careful with these two and try to learn the documentation part of it. So they have, both of them host online some documentations. Please keep it handy. Yep. And keep in habit of refreshing your knowledge on both of them every 3 to 4 months, because they keep updating it. They do a lot of updates.
Krishna, I have one question here. So as you said, these libraries keep on updating. So I was working on one library that is compatible till Python 3.5. So I'm able to run the similar code on Google Lab, but I'm not able to run on my Python because the library is not able to, I'm not able to install the library. So what is the solution out of that? How do we take care of this kind of problem?
Yes. So what you can do is, let us say this is the code that you have put your in Python, say 3 or 3.5, for example, and it has got everything onto that. What we can do is we can pickle this up. We convert this whole thing as a function, if possible, and we will pickle it up. That means we'll store this function and we will use it as a API. Get my point? So we'll define some inputs and outputs over here to the function. So say you have to give it input file as an input. So we have to name the file here, and that file has to be worked on. Yeah. So there is a function called pickling that I will show you down the line. That is the worst thing you can do. But if you can see, if it is unless and until it's Python 3, I don't think so. There should be a big problem. Did you check it up? Is it because of Python version or anything else is an issue there? Are you sure it's Python 3?
So, yeah, so I was watching a few videos on this particular library. So most of all those videos were on 3.5 Python or before that Python. So they were clearly saying that it should be, I'm working on Python 3.5 or 3.3 like that, and that's how we are installing it. So I have Python 3.7. When I am trying to installing it, so it is showing that it is not installing. So it is showing a lot of conflicts. So I'm
what
not
is the
able to
name
install
of
that.
the library?
I forgot the library name. It's related to Quandle. So it's related to Quandle.
Share the name with me. I have another machine with me which I use it only for R&D. Let me downgrade myself to Python 3.4 and then try. I'll not even 3.5. I'll go beyond that and let me try loading that. Let's see. Yeah.
Okay. I'll share the name of it. Yeah.
All right. Yes, there are sometimes possibilities like this. I'll give you one example. The chatbot that I made, so I got one request from Great Learning saying that we want to use only TensorFlow to build a chatbot. We don't want to use Keras. So what I did is, to use TensorFlow end-to-end without Keras, we have to use something called tflearn. Okay. tflearn is not compatible with latest version of TensorFlow because they have changed this library here. Yeah. So what I had to do is I had to downgrade myself, let us say from TensorFlow 2 to say TensorFlow 1 point something. And it is exactly like what Ashish said, as it is not working below certain levels.
So I had to actually come down to one level below that. And then this thing fired up. So what I did was I pickled it up. Pickle in the sense, I know this is going to be a problem. So I converted this into a runnable function onto any of these OS. It was not that easy because the files, the stuff has commands like import, tflearn. But if I'm using the current version of TF in my Python, definitely it's going to give me an error. Even this solution might not work that great. Yeah. So yes, since we are using something free, this will happen, and it has happened many times in my career where this is not working and we have deployed something. So what we have to do is we have to find a fix for that. All right. So Ashish, there are so many libraries. Yeah.
One more question related to this. So is it possible to downgrade the Python version or Tensor version without losing the previous data that we have worked on?
Yeah. That is a risk. See, if I downgrade, I just need to know if I downgrade, is it going to overwrite my, if I have a control of where Python is going and copying the file, if you know what I'm saying, in your C drive, it is going to create one folder. If it is going to overwrite my current folder, then yes, you will lose it. If it is not overwriting, if you have a control over that to create another folder, you don't worry about it. It's going to be as it is. It's all about a folder. That's it.
Okay. So if I save my files if I save my files into another folder and then try to downgrade it, then it would not have any impact.
Yeah, it should not be a problem. Yes, should not be a problem.
Okay. Would I find a simple code using Anaconda, or do I have to uninstall Python and then install it again?
I think you need to uninstall Python, and then you need to install the specific version, or if just look it out, just check out on Stack Overflow or Geeks for Geeks, any of these websites. Is there a place to run two of them? Because I'm using Mac, right? So in Mac, I have an option.
Okay.
The original Python that I'm running is 2, but I have an option to upgrade it to 7, so I can run both of them. Okay. In Mac, it is possible. So what you can do is you can have a Linux VM, or if you can have a virtual machine. I don't know whether you have done it earlier, but if you have a VM, you can do it easily. You don't have to worry about any of this. But if you are doing in Windows Live, I will say store your Python as you said, and then uninstall it and then reinstall the new version. This is what I know.
Okay.
But try to check on Stack Overflow if there is a command to have both of these versions and to choose which version to run when. I'm not sure about it. Yeah.
Hey, how much storage you have in your Mac, Krishna? It's a simple question. Huh?
128. This is 5-year-old Mac, so it is 128 GB.
Okay, even I am having the same thing. So we just thought whether need to upgrade or not. Okay.
No, it is working good. It is working good. No problem at all.
Okay.
But yes, down the line, if you talk about working on computer vision and all, then either you have to work on Colab, or you have to get a laptop which has GPU in it. Otherwise, your Jupyter is going to die. It will take 10-15 hours to just train your network.
Okay.
Yeah. But Colab is now, because of Colab, a lot of people are very happy. We don't have to spend money on GPU now. But I don't know.
If we go to AWS, it's we need to pay high, right? If we go to AWS.
Yes. Now Amazon, Azure, that is Microsoft, and Google, they are head to head on this.
Okay.
Everybody wants to conquer this space basically. That's the reason Google is giving it for free right now, so that they will get you addicted first of all for the GPU. They are giving a GPU which is 32 GB in RAM. Imagine the speed of it. And there is no Python dependency there. So you can go and install any version, anything there. You don't have to worry about what you have installed on your machine. There's no sync with it. That is what I like about it. But the only issue is TensorFlow and Colab. Both of them belong to Google. So I'm not sure how long it is going to be free, to be very frank. And now Azure is also picking up. I don't know whether you guys have heard about it. Azure is making an end-to-end analytics platform within their own cloud. So it's going to be a big rival for our AWS.
Okay.
Yep. So if you guys can work,
I had a conversation with somebody in the Google itself. So their idea of Google Colab is similar to Gmail. So they want to keep it as free as long as possible unless they have a
good
issue. Yeah.
Good. That's good for us actually then. We don't have to spend on a GPU machine.
Right.
Yes. Because one of my learners from the other batch bought a machine specifically with GPU. It costed him a lot actually. So, but then this collab came in, so it worked. But I feel there are some issues with collab also, that if it's running in middle, if it stops or your net fluctuates, no, it restarts basically rather than restarting from where it was stopped. There are some issues, but yeah, it's a beta version, right? So they will upgrade it. Okay. All right. So let's come back here. Let me show you one simple example of how to build a network, and then we'll close down the neural network part. Where is it? Great learning. Where is my defect prediction? Yeah. Okay, say I have a very simple problem where I have got two columns. One is some, number of days a person is working or a tester is working, for example. And I have another one where I can say these many number of test cases the person is testing in this many number of days. Yeah. And out of that, the outcome, the target column is defect prediction. So this is many of defects he is getting out of it. Yeah. Now, what is my business problem here is, what if I can make a predictor here saying that in future, if I give these two values, I should get an output like this. Okay. Let's try to build a model onto that. So what I've done, first of all, is I have used all of our machine learning techniques as usual, just to show you guys the power of machine learning versus AI. So first we are using decision tree, and since I have done pruning already, we are not getting any overfitting issue and everything is good as of such. Random forest is coming a little lower, which is 88. Boosting is 84. And gradient is around 90. And bagging is 88. So if you compare all of this, I feel boosting is doing pretty good. So we'll choose one of them. So we have made an ML predictor with accuracy of say 90%, for example. So this is a very simple way of doing an ML. So now somebody asked me, right, that this AI or deep learning is pretty good. Then why are we learning ML?
Yeah.
These are the things using which on a very simplistic level you can implement it. You don't have to, go ahead and do back propagation, forward propagation and all that part of it. So some of the applications, or I will say right now, at least for next 3 years, that is what is my prediction. If you guys get on a real-time data science project also in your company, the first 2 to 3 years, you will be deploying only these kind of things, to be very frank. Because if the company is new, if the project is new, and if the space is new, the company does not take a big risk of implementing high cost products. And when I say high cost, it includes GPU. It includes deep learning. It includes training time. A lot of things are there which we call it as KPIs for high risk projects. So what we do first, we penetrate into clients' trust by using these kind of simple microservices, and once they are confident enough, then we take them to deep learning part of it. Yeah. So this is one example. You can say that yes, this is where ML has an edge over DL. Simple levels. I don't expect to do image processing and all using ML. Not possible. Yep. Now, to counter this up, what I have done is I have made a very simple neural network which starts from here. So you can forget whatever we did above. No problem. We know that the above part. Next, what I'm doing is from Keras, I'm implementing a sequential library. What does it mean? if you observe our Excel file, the simulation, I'm sorry, not this one. The simulation that we did, don't you think this is sequential kind of stuff? This depends on this. This depends on this and this. It's like a sequence. So the first part to understand in coding is we have to tell Keras that our model is sequential model. All right. Next is what layers you want under Keras. So if what do you want under Keras? So to add a layer, to keep adding those hidden layers, no, you have to use the command called dense. Next thing, if you want to drop out and if you want to do normalization, even it's possible under Keras. So we'll do it. Okay. After that, we don't want sklearn, and one more library is optimizer. So this is used for back propagation or gradient descent or to adjust your weights, anything you can call about. All right. Now, let's go further. So as usual, we'll import the data. No change in that. We'll define X and Y. No change in that. The only thing you have to be very careful is even if the output is in the form of classes, yet you have to do a categorical out of it. Category in the sense you have to convert this into category, because if in case this looks like a category and it is not category, neural network is going to fail. So please be careful. The output, the Y of each and every data in your data set should be categorical, no matter it is test or train, whatever it is. So either you do it before split or you do it after split. After split, the only issue is what I made a mistake here is they have to write 2 different lines. What if I would have done earlier itself? 1 line was enough to categorize. All right. After that, coming on to the inputs. Now, can somebody tell me if I want to design a neural network here? Yeah. What should be my number of inputs? So I have to have some inputs, right?
2.
Sorry? 2. Perfect. 2 inputs. And what will be my number of outputs?
1.
Okay, I did not show you. There are actually 3. 0, 1 and 2.
0, 1, 2. Okay.
Right? Yeah. Perfect. So I'll have 3 outputs. Now, if I have 3 outputs, what activation function I should use? Softmax. Please remember that. No more relu and signal. Okay. So this is the input and output we designed. Now let's try to focus on the interior part. So before that, please remember, till you are confident enough to visualize all this, always print the shape of your test and train. So this will help you to design input. This will help you to design output. Got it? 3 outputs, 2 inputs. So the first thing you have to fire up is you have to tell Python that this is a sequential model, and the name of the model you're defining is model itself. And every time you make a change now, you have to say model dot add. What I need to add? I need to add a dense layer. What is that dense layer? So first of all, this is your first input layer. Now in input layer, what we are doing is we are considering input layer itself as a neuron. So you can say that yes, we are having a neuron here and we are giving input to it. So you can consider directly this as an input. Sometimes we don't take it up. Sometimes we start in new activation functions from hidden layers. Yeah. In this case, what I've done is I am saying I want an input layer of dimension 2. That means I need 2 neurons and I need 64 weights. Now, if you ask me why, because my next layer is having 64 neurons. So if you remember, each neuron is supposed to be connected to other one. So like that, if I have 64 inside, I should have 64 lines of weights also. Agreed? So this and this should be in sync. Next is I'm saying the activation function I'm going to use is relu for now. Now coming to okay, so please ignore dropout because this is the topic from 3rd week. Dropout means it switches off some of your neurons. Okay, it's a type of hyperparameterization or feature engineering in a neural network. So please ignore for now these 2. Next is I'm saying is I will add another layer, that is my hidden layer, such a way that it will have 64 neurons and activation again is relu. And the 3rd one is your output one. So output is I'm saying is I will add 3 layers. Sorry, I will add 3 neurons as an output. Activation by default is softmax. What if I have used relu here? I will get a regressed output. If I use softmax, I get a classified output. That's it. All right. So this is your neural network on a very simplistic level. 1 layer, 2 layer, 3 layer. It is capable enough to deliver the same what ML gave us above. Next, so we have created a hardware. So I can say we have created an empty network. Now we are supposed to populate it. Now how do I populate it? Before populating it, we have to design back prop. So I can say this is forward prop. This is your back propagation. Back propagation is nothing but optimizers. So there are so many optimizers available. So if you want to see the list of optimizer, you can just go to Google. Keras optimizers. Okay. This is the documentation which will help you to understand all the optimizers available within Keras. I will show you each one in each case study. Okay. RMS prop, ADA delta, ADA grad, Adam, SGD, all of them I'll show you one by one. So for now, let's talk about a very simple optimizer, which is Adam. Now, if you ask me what is optimizer, very simple. Remember, dou L by dou of weights. The formula or the person who does this is this particular person called Adam. All right. Instead of Adam, you can have SGD, RMS prop, ADA, grad, a lot of things we have. Depends on the application what we are choosing. In this case, it's a very simple numeric application. Adam works the best. It is something like a ReLU, a generic. You can trust him for all the back props. And also you have an option to define a learning rate. So that is, I keep it usually in 2 decimals, 0.01. If you want to be a little slow. If you want to be very dynamic, you can put large. But if you have a large activation function, please remember, we just discussed, it is going to oscillate. It will not come to a rest point. But yes, your neural network training will be faster also in the larger learning rate. So this is your Adam. Now you are saying, this is my model. Please attach this optimizer, which is called Adam. The loss, the way he is going to calculate loss function is nothing but it is a categorical data, and we are going to use cross entropy. Guys, what is cross entropy? We know entropy, right? What do you mean by cross entropy? Have you heard, or have I told you? I think I have not discussed this before, right? We know entropy. All right. So I'll do one thing. In next session, I will give you some mathematics behind it, and we'll try to see 1 or 2 Python examples. So there are so many loss functions available in neural nets. One is called cross entropy. If the data is categorical cross entropy. If your data is sparse, what do you mean by sparse? There are a lot of zeros as in the output. In that case, you can say that yes, it is sparse underscore category underscore cross entropy. You have multiple of them available. For now, whenever you see category, use this one. This is the best one. Post that, what should be your checkpoint? So I am saying accuracy will be my checkpoint. Do we know any other checkpoints? We know precision, we know recall, we know support, we know F1 score, right? So this is what you can use. Always, I will say, use accuracy. Accuracy is a very reliable factor so far. Next, what I do is, so my back prop is ready, my forward prop is ready. Both of them are ready, so you fire it up. As usual, from your machine learning, fitting. So just take the model, fit it. Fit onto what? Your training data. Okay. Batch size. Now this is something new. Batch size means if your RAM is capable enough to fetch the input at a time, I would like to fetch input for next 80 readings. You know, so if you have a good RAM, even you can put 800. So if you are doing computer vision, image processing and all that, we usually keep batch sizes very big so that the fetching is faster. In this case, you can choose any random value you like. It's something like our seed, if you remember, random seed. But here it is about fetch executions. Next comes your epochs. Now what is epoch? Please remember, 1 epoch is equal to 1 forward prop plus 1 backward prop. That's it. Now you may ask me, fine, how do we choose this up? So what I would say is, first of all, you choose single digit epochs, say 5, 6, 7 like that. And once you do that, look at the first 5 epochs. So let us say these are my first 5 epochs till here. Look at the loss function. Yeah.
Can I say it is having a huge amount of change? Do you observe? There is a considerable amount of change. A difference of 2 is huge enough. So if you find in first 5 or 10 epochs that the changes are very huge, then you say, okay, let's use 50, 100, 200 like that. Or else you can check the accuracy. If you find the accuracy is continuously increasing by a good number, then you say that yes, if I have more epochs, more accuracy I'm going to get. That means more number of epochs, more backprop, better the weights, nearer your accuracy, or I'll say nearer to 100 is your accuracy. So in this case, when I ran for 100 times, I got an accuracy of 84. It is not as good as ML, because in ML we got 90, but this is a very dynamic model. What does it mean? Tomorrow when my inputs change, let us say, it takes no time for me to retrain this. I know even our ML takes no time, but in ML we have to do hyperparameters and all those things, feature engineering, and we have to take a lot of pain to again redo it. In this case, it will auto take the changes and auto adjust the weights, and at the end it will try to show us results somewhere near those. There are certain weird cases where you might find ML has an edge over this, yes, but more or less deep learning should be good. All right, now what do? Let me show you what is softmax. So if you remember, the output was softmax. How many? 3 of them. So look at this. This is the predicted output that we have got. Now what are these? These are nothing but your probabilities. Softmax will pick up. So all 3 of them will get a probability. So let us say if I have given an input and I'm expecting answer as 3. That means 1, 2, and 3. So softmax will give me a probability. What is the probability that the answer is 3? Let us say the probability is 0.9. This is 0.7. This is 0.3. The softmax will pick up the neuron which is having highest probability. So just to show you guys, this is the probability that we have got. And if you see, the highest probability belongs to this particular person. So the answer is 0. So my classes are 0, 1, and 2. All right. You don't have to do this, just for your showing purpose of softmax. That's it. And finally, you do your testing part of it. So you take your model and run it or evaluate on your test data. So when you do it, I get an accuracy of around 88. So which is a little more than 84, I know. So what we would have made a mistake here is why it would have shooted up high is because of a batch size or number of epochs or learning rate. So you can go back and just adjust it somehow. So I can say that yes, this works good. On my testing data, I got an accuracy say of 88%. Perfectly good. So this is how you can train a very simple neural network. So I will again request all of you is pick up some of your machine learning old data and try to build a model like this and see how you are getting, and then try playing around with more layers. So now if you want to add one more layer, what to do? Very simple. Copy this, put it. Now when you put it, you can keep the same number, not a problem. Now you may ask, okay, how did you get 64? There is no logic for that. So what I do is, say I start with some number, say I would have started with 100. If I have 100 weights, my next layer should have 100 neurons to take it up. If I want my numbers to diminish, I will say my next layer will have 50 neurons. You can have one more hidden layer here saying that my next layer will have 25 neurons. If you want one more, you can say my next layer will have, say, 50 neurons. You can double it up, not a problem. And from 50, it will converge to 3. Your wish. All right. So some of my other batches is also asking me if I can give some mathematics behind it, how to design this. I will again say there is no proven math that how to choose these numbers optimally. But yes, I have got some links to some blogs where they have done some equations, but that is specific only to their data. So you can just take some learnings, and more or less, this is the way you identify. Clear? So try this up on your old data and let me know how comfortable you guys are on forward and back prop. All right. So I am done. So I think we have covered for 1.5 weeks now, because forward, back and all were part of our next week, but good. I feel if I show you something, you should also understand. So I don't want you to miss out anything. Yeah, so I think we are going good. We'll almost complete everything by next week or by third week starting. So we'll have some extra 1 hour. I'll try to show you some deep learning, more networks onto this. Yeah, image classification, text classification, all that we'll see down the line. We'll do some social media analytics and all those things using deep learning. Okay, good. Any questions for me? Or we can close.
Krishna, just one question. Unless and until we find out the correct number of hidden layers, do you feel that ML is going to have advantage over AI
Yes.
deep learning? Huh?
Correct. So what one of my learner did was, he is very ambitious enough to find the answer for this. So what he did, he did grid search on this. He said, grid search, he put lot of layers. So let us say in grid search, he said, okay, one number of hidden layers could be 10, it could be 20, it could be 40, like that he started. And he ended up spending 2 or 3 days for the neural network just to run and complete the grid search. Okay. Yes.
Okay.
You're perfectly right that if we are confused about, or if we have a very, if you don't want to take the pain of mix matching this stuff up, yes, ML has an edge onto this. But ML cannot work, or I will say supervised learning cannot work onto computer vision and NLP. So by default, this is the only backbone for image processing and text processing. Okay. Yes. So anyway, people come back to this, but yes, if we don't have time to and patience to basically do this, you have ML has an edge onto that. I agree with you perfectly. And I am clearly saying here, in this case study, I still feel boosting is having a big edge over the other one, because it's a very simple algorithm. In 4 to 5 steps, it is giving you everything. Whereas in ML, we had to do a little bit of an extensive part of it. But on the long run, this is far better, I feel, because it auto-corrects, auto-learns itself, auto-corrects its own weights also. Yeah.
Okay.
So again, to summarize very quickly, the whole game of neural network is to adjust their weights. That's it. How do we get these weights? We will do in week 3 what are different type of weights. For now, please remember, weights are random. But also we have a provision where you can control your weights. We will see down the line in your 3rd week when we do hyperparameters. All right. And second thing is, there is 2 type of propagations happening: forward prop, backward prop. Forward prop is to spoil your output. Backward prop is to adjust your output or adjust your loss function. Good. Next is, you have 3 layers: input layer, which should be in sync with number of columns or features available. Output layer should be in sync with total number of categories you have on your output column. Good. And the hidden layers, again, is a big myth. I will say start with a number like 100, 120, 150, and then keep reducing it, half it, or divide by 3 or divide by 4, whatever you like. But yes, it's a cumbersome process. If we don't, in one shot, see, I got this. But not always we can get an 84% accuracy in a shot, to be very frank. And still I stopped at 100. You know, if I'd have gone further, I would have got at least 90 plus accuracies. Yes. So this is the overall summary for neural networks. That's it. Good. So now can I say the concept is little, the burden has gone a little less on the understanding part. Now I think if you go back and watch the videos, no, I think it will make more the theory what professor is explaining would be more interesting, you know.
Yeah.
A little more understanding maybe.
Yes. Okay. Then wait for computer vision. Computer vision is going to go on a different level again.
So we may need to use glasses to correct that vision then.
Exactly. Yeah. But yes, if next 5 to 10 years, no, they are for deep learning. So last 10 years were for machine learning. Now the era has come for deep learning. Because you remember I showed you guys auto ML. Do you remember that code, which will auto take our inputs? I don't know. Some of you were there with me.
Yeah.
I think some of you.
Some apps have shown Camel was the thing.
Auto ML, yes.
So you can easily replace a machine learning data scientist who knows only machine learning with that piece of code. If you want me to show it again, I will show you guys again that thing. So already in my work and some of the codes that I do here for my newer batches, I already use AutoML onto that. I don't need to code anymore. I will use AutoML to get my predictions out. And it is becoming very common now. Even Google has come out with something like an AutoML, which is similar to that. Azure already has it. So now, if you want edge, yes, deep learning is the next one, because we do not have AutoDL as of such. It'll take some time to come ahead with that. Okay. So take it in a slow manner. We don't have to rush. That's the reason we have designed this particular module, so that you get adjusted to neurals. And we will go, or we will run basically from computer vision. Next module. All right. So please understand each and every factor here, and don't miss any minute details. Also, any issues, anything, drop a post on your group. I will try to answer that. Yeah. And what I showed you today was very simple. Next session we'll scale it up. We'll try to design more complex models. Okay, I'll show you something onto text and image processing also right away in next session, so that you get a good feel of not only categories and regressors, but also other two. But I'm not sure how many of you will use this for regression and categorization, because already you have ML for that. So the edge comes in, something onto image detection, face detection, expression detection, sentiment analysis. A lot of things you can do using that.
But anyway, we will not use neural networks for this detection, right? We'll use convolution only, right, Krishna?
No. I will show you. So your first project for neural network, we will make you use KNN for image processing or image detection.
Okay.
If you use deep learning also, yes, and you are perfectly right, convolution is the default one, but we will make you use neural network to detect an image. And opposite to that, we will make you also do KNN to detect the image. And then the reason we do it, just to show you the difference between ML and DL. Even we can use SVM to detect images. Or I can say not detect, I will say classify images. So if I give you a number 7, let us say you have an image screenshot, and that image has something like this. I can use SVM to identify what it is and display this image represents number 7. We can do it. Yeah.
Okay.
But convolution is a better way to do it. So we'll see in next module why it is better. What makes convolution better than neurals. And even we have better version than convolution. We call it RCNN, Regional Convolution Neural Network. We have more better version than that. We call it YOLO and SST. And it's still evolving. We are not happy with that also. It's still evolving around. So we are going to do a complete 8-week session or 8-week module onto computer vision. It's a very long module. We'll spend 2 months onto that. All right?
Okay.
Perfect. So I think there are no questions. Let's move out. So Ashish, I'll take you to your code. And I have a very similar code to that. I can help you to give that. It also does the stock prediction only. But 1 minute. Predict the next 10 days. The model is basically predicting values for the range of data I provided. I want to predict the future values. Okay. So you are using LSTMs here, right? I saw you have used LSTM, right? Yes. So is there any issue here? Because I did not run it through as of such. So
if you go to the bottom of the code, there is a chart that I've made it. If you go to the bottom of the code, there's a chart. So basically what is happening, if I see the chart itself, what is happening is this is the event that happens in the market, and the code is reacting to the event in a delayed format. So for example, let's say on a day 4 or 5, the blue line, if you see, it peaks out, and after that the red line also peaks out. So it is happening in a delayed format. So it is just repeating. It is just predicting what has actually happened, not predicting the future.
Correct. Got your point. Okay, then I need to analyze the whole code step by step. Why it is happening. So are we missing any values here, or the network is an issue?
we need to check this because
So
it's a
the
very
values are
complicated.
complete.
Okay.
I have all the values of the data. The data is complete, but I'm not sure about the code because I just borrowed it from various places and we tried to put it together.
Okay. We'll do one thing, Ashish. I have a solution for this. Meanwhile, I work on this, correcting this code. I will give you one more code of mine. So just between us, okay? So you can just modify it and then use it. Give me a minute. Where do I have it? I have it under LSTMs, yes. So go to I go to top documents, data science, contents, deep learning, LSTMs. Yes. So I have something like this which predicts stock markets. Yeah, it's a little customized code. So it is almost similar to what you have done, except what do I have here is I have got a huge amount of corpus. Now, if I show you the corpus that I have, might not be exactly same as yours, but you can use it. 1 minute. Deep learning, LSTM, time series, stocks. So this is what I have. Okay, and this is the way each company's stocks are there.
Okay.
All right. So what I will do is I will share this code with you. It is a self-explanatory code. If you know LSTMs, then I don't think so it will be an issue for you. What I am getting is I am getting yes next 18 or 20 days of prediction. I am getting it. So this is my prediction basically. Yeah.
Okay.
So try this out. If you are able to take some contents and fix it. Parallelly, I will work on line by line of this because I need to understand the whole flow. First of all, it's not a simple, task. Second thing, I need to train this up. Because usually what LSTMs do is, LSTM has two parts. I don't know if you know this. LSTM has got two parts. You can use LSTM to first encode and then decode. So I'm not sure if you just used it for encoding part of it or have we put a decoding layer. I think it is just an encoder basically. Okay?
Yeah.
So let me go one by one. Let me optimize your code and then let me analyze why that 10 days or whatever gap you are saying is happening.
Yeah.
All right.
And one more thing I want to include in this code that I think would be significantly helpful is to incorporate other features. For example, big file.
Yeah.
So other features would be able to help us predict the stock price better. So if we can include it, because most of the LSTM code that I saw on the website, they only predicted on one value, either on the closing value or the opening price. So if we can include other features, that would help us to predict this price in a much better way.
Okay, perfect. Let me check it out. Okay, so I'll do one thing, Ashish. First, let me solve this problem because it looks like to be a complex. I'll not say a very complex code, but yes, when LSTMs are involved, it is little complex. So first, I need to understand the design of the network. First of all, why it's 50, 60, 70. What is it making this way? And probably once I get hold of it, I don't think so it should be a big trouble editing this. Okay.
Cool.
And parallelly, I'll share this with you, my code of LSTM predictions. Check it out.
Okay, that would be helpful. Yeah.
All right. Perfect.
Yeah.
Good.
Cool.
Okay, Ashish, one more thing. Just a reminder. There is one guy called Ganesh who has just joined our batch today. He has he has what do you say? This is a little difficult way to do time series, to be very frank. Because tomorrow if something changes, you have to train your network, and I don't know how much time it took for you. I think the epochs are not that heavy. Yeah.
No, it actually took me around 1 hour to train this code.
Correct. Now, just imagine tomorrow if the backend content increases, the training time will also increase. So first option, what I would request you is, if you are deploying this somewhere or if you're doing for your own knowledge, perfectly good. This is very good. But if you're deploying it, just
the intention
check the
is
cost.
to deploy it eventually. The intention is to deploy it eventually.
Yeah. So just check the cost of it. Cost in the sense, because whenever you have to retrain your model, you have to retire your initial model first. Then you have to pull it back, and then you have to retrain it, and then push it back. So that a non-operational phase, you have to calculate the cost for. So if you are okay with it, no issues. First option should be ARIMA. Second option should be LSTMs, to be very frank.
So
Right?
the reason I train it on a daily data is that because it would not involve too much cost in execution, because I can take the manual decision after it predicts the data whether so my intention was actually to do it on a live data, on a ticker by ticker or a second by second data. So that would
Mhm.
be I'm not sure, because if it takes a 1 hour to run the code, it would not be possible to do a trade on that kind of data, on a live data. So
Hmm. Hmm.
that's what I was thinking. So
Correct.
is the deployment different from what we are doing? So first we are trying to create a code. Once we are
Hmm.
satisfied with the code, how the
Hmm.
deployment take place? How is the deployment say start?
Correct. So where you want to deploy this?
So
Where
I
you want to
would like to
deploy it? On a web?
deploy it on my broker account. So using my
It's
broker
a web?
account, I would yeah, it's
No,
a
no, it's a
web
web
based.
or web. Okay, I will show you right away. It's a web, right?
Yeah, it's a web.
Web, right?
Yeah,
Okay,
it's a web.
fine. Let me show
Yeah.
you. Yeah, let me show you right away. This is not our LSTMs, but yes, this is one. 1 minute. So we use Flask basically, Ashish, to do this, and I will give you
Okay.
this code also, so you can deploy it
Okay.
immediately. And this is my app. So the overall architecture, if I show you, just give me a minute. So the overall architecture is that my intention is here to make a HTML web, which I have done it. Okay. So this is my HTML and this is my CSS, some styling I've done to create an interface which looks like this. Okay.
Okay.
And this particular thing is very simple. You have to just put a URL here. This URL will be given as an input to me in my code. So I use Flask to convert whatever I'm talking in Python with respect to what HTML and CSS understands. Very simple. So I'm taking a link from a user via Flask. I'm inputting it into my model, which is pre-trained on some kind of data. It's a neural net model. Okay. And after that, I'm saying I'm replying back to the HTML using Flask, saying that it is a real news or it's a fake news. That's it. We are doing it. All right. Now, how do we do it? Let me show you the code. The code is very simple. Let us say, if I can run this before that. Yeah. So this is the Flask app. So there should be one application which you have to make it. So after you are confident with your model, what you have to do it, you also pickle it. If you see this is called pickling. Pickling is like converging your model and storing all the supporting files onto a location which can be called from anywhere. So this is my pickled package, which is nothing but my naive-based model that I've designed above. Okay. Any model that you design could be pickled like this. So this is the two-liner code which you can use to pickle, and once you run it, you will get a pickled file like this. Now your job is to import this pickled file in your real app. So this is my real application. And also parallelly, I have deployed a web page. So this is the link to my web, and this is the CSS which I have written on that, basically some styler. So whoever is handling your application will be having access to both of these. So where your website is hosted, there you have to go and drop this pickle file basically. Okay. Along with this pickle file, there is a code. So this is what we call it as Flask. Now what does Flask do is Flask allows me to create an app. Inside that app, it allows me to load my model if I have one. This is my model that I pickled, if you remember. Next is it allows me to connect my HTML page link here. If you have an IP or if you have any other thing, you just put it across here. Next is what you want to do with it. So if this is the HTML page, what do you want to do with it? So my HTML page, what I want to do is, let me run it. If it is not, okay, it's not active. So let me run the code and I will show you. It'll take some time. It's not that fast, but yeah. So you just have to run it once. That's it. Once it generates an IP, yeah, IP is ready. Look at this. This is a fake news predictor. All I need to do is I just need to go and, for example, let's say, we'll pull some junk out of it. I have to just get the link, go to my web, publish the link here and say predict. It might take some time. the news is real. So this is how I am telling my app that first of all, this is the model that you are supposed to use from Python. This is the HTML page, and inside HTML page, what you are supposed to do, you are supposed to get my text. This is called web scraping, if you have heard about this term. Web scraping is like converting the data on the web onto an understandable data which could be passed to our Python model. Something like a data set, input data set or database. Yeah. So this is your web scraping. So whatever you want to do with your inside your HTML, you have to define here. So in your case, what you have to do, you have to publish a graph or give some numbers. So that logic should come here.
So no, actually, in my case, what I want to do is to give an order. If, for example, a model is predicting that the stock price would go up, so to send the order to the broker account that to buy the share, and also send us a simultaneous order giving a stop loss or a target price order, so that some execution can take place. And then when the model says, yeah, it's time to get out of the market, then it executes the sell order and exits the market.
Perfect. So in that case, Ashish, you will need a help of a web developer basically to write this interface.
Okay.
If we can do it in Python, as in Python should output, then no problem. We will say whatever is the Python output will display it here in this chunk. But if in case a lot of interactions are needed internally, you need a web developer to take you through those interactions. Because I'm not sure I'm not that good at HTML, or I'm not sure even you are, but the person who has designed the web should be good enough to put the interfaces.
This brings us to the end of this tutorial on machine learning with Python for beginners. So folks, thank you very much and have a great learning ahead.
Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. Show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.